Okay, so unfortunately today I'll have to leave before 4, so we'll do just, let's say, an hour and 3/4 with no break and stop there. Okay, so where were we in the end of the last lecture? We wanted to calculate the behavior of the simplest quantum system that one can think about, which is just free particle. We have shown that the Hamiltonian, which is just px squared divided by 2m, commutes with px, and therefore the eigenvectors of the Hamiltonian are the same as the eigenvectors of the momentum operator. Unfortunately, the eigenvectors of the momentum operator don't live in Hilbert space, in a relevant Hilbert space, for the simple reason that we can't normalize it. We use the trick of Dirac delta function, but still, if we'll take this wave function squared and try to normalize it, it won't work. So, what is the answer? What is the solution to this conundrum? The answer is you basically can't find the electron in a solution of the Hamiltonian, in an eigenvector of the Hamiltonian. It's always some wave packet comprised of several values of px. You have a superposition of states there, or a wave packet. Not a situation that's unheard of. Also for photons, you never can have in reality a single photon. For the simple reason that, again, you can't normalize the wave function. Again, you create a wave packet, which is relevant also for technology. When you're transferring on a fiber optic photon, you're saying that you're not really sending a photon with a single frequency. You create a wave packet, which has a spread of frequencies. Okay, so basically we wanted to see how is the time development of a wave packet which represents a single particle, single free particle, and we wrote down a Gaussian wave packet, which I'll just rewrite. Okay, and I explained this normalization in the previous lecture. integration over a gap. Okay. Now, how do I study the time development? We want to find out so one thing that we can do is solve the Schrödinger equation with this boundary condition. The other way is to decompose it to the eigenvectors of the momentum and use the connection between eigenfunctions of the Hamiltonian and the time development, which we introduced in one of the previous lectures, and that's what we are going to do. Okay. So we want to write down why this is the eigenvectors of the momentum. This is some amplitude. And basically, we will find out what is AK out of the behavior at time 0. Okay, let me rewrite it. And I have to perform this integral. I'm integrating over x, and I have here square of x and a linear term in x. How do I solve this type of integral? I'm sorry, the last lecture and this lecture will have a lot of mathematics. Square. Yes, exactly. We'll write it down as a square, and a square we know how to solve. So, Why? Because when I square this term, I get exactly what's written here. But I get an additional term of k squared delta 0 square, so I subtract it. Okay. This term doesn't depend on x at all, so I can move it before the integral. Okay, how do I make sure, how do I convince myself that I didn't do here mistakes? The easiest way, or at least something that you always should do, is, and just a moment, you check units. Remember, k is 1 over length and delta 0 is length. And always terms have to be unitless. Okay? Squared and 1 over squared. Let's take here 1 unit of length. Here I have 2 units of length divided by 1. Fine. So I have 1 unit of length squared, 2 units of length divided no units. So I could have still here performed mistakes in factors 2 or something like that, but at least the unit-wise, I'm okay.
So your school, that's for the units, right? Like
I'm not sure I understood the question.
This here comes for units because
No, here
you can.
Here, of course,
Okay.
okay.
Yeah.
So somehow I forgot to write it down there, but very good. You saw that the units are wrong, and that's how you find out that there's a mistake. Okay. Looks somewhat still miserable, but we'll just change variables. I don't care that I have there an imaginary part of the constant. It doesn't change anything. And basically I can replace this by and that's an integral which we solved in the previous lecture. We can mistaken. And we end up with a result and basically we got what we expect, that the Fourier transform of a Gaussian is a Gaussian. Here it's a Gaussian in K-squared. Okay. What is delta K at time 0? The uncertainty in K, which is the variance. Okay, variances of Gaussians is easy. You could go and write down the integral here and find out, but we know exactly the result. Which tells us that these Gaussians give us the minimum uncertainty in the combination of, well, momentum and space. So this is the wave function of minimum uncertainty. Okay, but we started this game trying to answer what is psi x of t. We found AK. So we are able to write the full solution, time-dependent wave function. What should I do? Because this is an important point. It returns again and again in different problems. Well, if I know the eigenvectors of the Hamiltonian, and these are the eigenvectors of the Hamiltonian, all I have to do is add phase, which depends on the energy, and integrate. We have shown that at least twice previously. Okay, so I'll do it exactly. So, it's an integral, not a summation just because it's a continuous variable. AK, which we spent some time on calculating. Okay, so that's the general solution for any problem. The only thing that's special here is that, and I have to add, of course, the eigen. What is E?
The energy is
Yeah. What is it? It's a free particle, Tom. What is the energy of a free particle? We calculated it, but even without calculating, you should know.
The kinetic energy?
It's the only energy that a free particle has. That's why it's called free. So,
Zero.
what is it?
zero.
No.
Have the mass v squared.
Yes, but we don't use V here. What do we use?
P squared divided by 2n.
Exactly. P squared divided by 2n, which is h squared k squared over 2n. So I'll write down all terms explicitly. I'll copy the amplitude from what's written here. Okay. Looks very cumbersome, a lot of terms. But at the end of the day, I have here only dependence on k squared and k in the exponent. Again, writing it down as a square of k plus something, I can solve this integral. It's a bit more cumbersome because 3 terms, not 2 as previously, but okay. And should have mentioned that I missed the Dirac normalization, 1 over square root of 2, so I write here also times 1 over square root 2 pi. And in order to save some writing, I defined now what will I do? Same trick as before. Define this guy as u, perform the integration. So, color. Call this guy u, perform the integration. And get so someone can tell me what is the physics behind this wave function? Starting to feel that I have your internal discussion with myself. It's the same form that we had before. Before it was your delta 0, some constant, some width of the Gaussian at time 0. It's still a Gaussian, But now the width changes with time. So the Gaussian wave packet has a very nice property of continuing to be a Gaussian at any time, but with a time-dependent width. So basically what happens is that if I started with a Gaussian at time t0, after some time, still have a Gaussian, but it's wider. Now, pay attention that this is the wave function. If I would like to ask what is the real space representation, I'll tell you secretly that it's still a Gaussian. But pay attention that if I want to write down the real space distribution, I have to take psi squared. And delta depends here on, has an imaginary part, so one has to do it carefully. It doesn't change the conclusion, but if you're doing the calculation to describe the real space distribution, you have to do it correctly. Okay. So, at this point, we know everything that there is to know about a free particle. Basically, its eigenvectors are the momentum eigenvectors, no big surprise here. Before we leave the interesting world of one-dimensional problems, what can we add to a free particle?
Potential?
Potential. Okay, so before going into solving particular cases like the square well, the finite square well, the harmonic potential, that's more or less what we will do, I want to give you some general properties of one-dimensional potentials. So I'm drawing a general potential. Could be more complicated, but this is just an example. Basically, I have here three different regimes of energies. Let's assume that V You have the behavior at v going to infinity, at v going to minus infinity, and let's assume that we have here a minimum. I could have all kinds of behaviors from several local minimas to maximas, and we'll discuss all kinds of variations. But in general, the most important thing here is that I have basically three regimes. Of course, I could have reflected it, all of it, just arbitrary that I chose v minus larger than v plus. Okay. What do I know about each part of this spectrum? So, in this regime, I have a continuum my energies there are not discrete, the same as for a free electron, basically because it's free, it's above the potential. And I have a degeneracy What do I mean by a degeneracy of 2? The behavior for k plus and k minus, for k going in this direction or that direction, is the same, but so the energy is the same because it's k squared, but it's two different eigenstates. Degeneracy is how many, for each eigenvalue, how many different quantum numbers do I have? And in this case, it's 2. Because going to the right or going to the left have the same energy, but they are different eigenvectors. So I have a degeneracy of 2. In this regime, I still have a continuum, but since I have to, there is already a difference between going to the left and going to the right. That's because going to the right, everything is open. Going to the left, I run into a barrier. So I have no degeneracies. And in this regime, I have discrete states. Discrete and, of course, no degeneracy. Okay, what will I have in this type of behavior? Exactly the same with three regimes. Basically, if this guy would go to infinity, so I won't have a continuum regime. If the value of v plus and v minus will be the same, I won't have a continuum with no degeneracy. That's all. So once we approach 1D potential, it could be mathematically challenging to find the solution, but if it doesn't correspond in general to this behavior, I made a mistake in the solution. Okay, so that's one general statement about 1D potentials. Check your degeneracy, check whether you're continuum or not, and it must correspond to such a behavior. Well, it comes out, it could be proven, I won't go into the details, but it makes complete sense. If I'm above the potential to the left and to the right, it's like a free particle. It doesn't behave exactly the same like a free particle, but from the point of view of continuum and degeneracy, it's the same. If it's in one direction, I have to create here some superposition of left and right to kill the behavior going to the right, the boundary condition. And here I have to use both of them to kill the wave function here and here. Okay, another general thing that I can say is on the behavior of the wave functions in the discrete regime close to the ground state. So I'm in the continuum regime. I don't care exactly what happens higher up. I have discrete states. I'll have some ground state, first excited, second, and so on. Again, I'm taking a mathematical proof and not giving the details, but it gives you a result that is very useful for checking if you correctly solve the problem. And the statement is the following. That's known as the oscillation theorem. Number of times that I cross x, y equals 0. What does it mean? Basically, let's look on a problem that you have solved already in modern physics. Infinite well. And in a moment we'll show it explicitly. And here's some normalization. Okay, we will do it in details, but because this form is known or not. So it's in this form. So the first solution that I have is, of course, n of 0, which gives us just some constant. How many times does it cross the 0? 0 times. The next solution will cross 1. So, first solution is just this guy. The second solution is this guy. This guy crosses once, and so on. So, first we can see it for all solutions. Okay, another very general statement about the behavior of one-dimensional potentials, and this actually I'll prove and introduced you to an interesting concept. if the potential has parity, okay, a lot of the potentials that we consider like the square well, the harmonic potential has parity. So I'm now going to define an operator. What does an operator do? We have seen it already a lot of times in this course. Takes a wave function and returns a different wave function. Okay. Let's define the parity operator. Now I claim that this is an observable operator. Looks like a very abstract type of operator, right? But it's measurable. How do I show that it's measurable?
It has a real eigenvalue?
Yeah, which means it's a Hermitian. I don't need even to go into its what are if we will, but okay, let's prove it. Okay. And use its eigenvalues. Okay, this is as long as I don't say anything about lambda. This is generally true. I operate on a wave function. I get a different wave function times an eigenvalue. But here I'll see what happens if I operate twice on psi. Okay. By definition, if I operate, I switch the wave function from x to minus x, and then switch again, I return to the same. So this must be equal to psi x. So lambda squared must be equal to 1. So lambda must be either plus or minus 1. Why can't it be some phase?
Because it's will supposed to be. Like,
Excuse me?
because it's will thing and not.
No, I don't even assume anything about it. It's just I operated here twice, so it's lambda square. It's not absolute value lambda square. It must be plus or minus 1. So So I have two eigenvalues which have their eigenfunctions. Excuse me?
Why it's even parity or odd parity?
So that's just associating a name.
But you associate the name just because you want it, or you had some...
Well, if I'm taking x, turning it to minus x, but it remains the same function, it's even,
Yeah.
by definition. If I take minus x and it gets to minus psi, that's an odd function. Let's go back to 11th grade or somewhere where these concepts were introduced. Okay. Now I claim that if I want to now prove this point, what does it mean? It means that if I can prove that the Hamiltonian is commutative with the parity, I can write down bases which has the same eigenvectors for both of these operators. And therefore, the eigenvectors of the Hamiltonian will have a definite parity. Because this is the form of a one-dimensional Hamiltonian with some potential. Now let's see what happens if I operate on some wave function. I just wrote the definition of a commutation. And how do I work with parity? Okay, everywhere where I have x, I'll change it into minus x. That's a definition. Okay, so I just have to write explicitly where I have x in p squared. Will be minus h squared divided by 2m right? I just write down the Hamiltonian, which is p squared, and p squared is dou squared to dou x squared constants, right? Yeah. Okay, this guy is squared. Nothing happens to it. Yes. If I change x to minus it. So I still have p squared over 2m plus v minus x and here I operate only on psi, not on the Hamiltonian. But Vx is equal to V of minus x. So it's equal to 0. If the commutation between an operator and the Hamiltonian commutes, so we can write a basis for the Hamiltonian, which also is also a basis for this operator. And since this operator has a basis that's either odd or even parity, so the Hamiltonian will have solutions which are only with odd or even parity. Okay, so first explicit form of a one-dimensional potential will be the infinite squared well. So the potential goes to infinity. Let's define 0 and L on the x-axis. It goes to infinity at 0 and L. Anywhere outside, it will be 0 because the potential there is infinite. So I have to have here something that will go to 0 at x equal to 0 and x equal to L. We have already met it several times. Sines. Good. But we forgot to normalize it, and if I normalize it, I will get here integral on sine squared. Just insert it in order to get the values of energy. So what do we get here?
Energy levels.
Excuse me?
The levels of energy.
I have first of all discrete values, must be, because both sides go to infinity. And the separation between the levels grows as n squared. So higher up, we have to move to higher and higher energies in order to encounter the next eigenvalue, next energy. So levels are dense below and become more and more separated higher up, just because it goes like this. Very different from the hydrogen atom, where everything bunched up close to the zero. It's basically because there we are in a 3D system, here we're in a 1D system.
Also, in a hydrogen atom, it's like having, it's instead of a two, well, there's one of them that's free.
No, hydrogen atom, although they plotted the potential this way, this is only in R. You have tit and phi that in any direction. So you still have three quantum numbers. We'll do it exactly. Okay, so that's the easiest, the simplest case, but it's not a typical case. The typical case will be a harmonic oscillator. Why is that? It comes from a very simple mathematical fact. Any potential, like the potential one that I have plotted previously, something like that, close to the minimum, okay, it will be its value in the minimum, and if I Taylor expand around this point, so to first order any potential that has a minimum is a harmonic potential as long as we are not moving too far from the minimal point, or to first order. That's why, in principle, the harmonic potential is very important, because nearly any problem in physics at some range of energies behaves similar to harmonic potential. Okay, so find the solutions, the eigenvalues of the Hamiltonian of harmonic harmonic potential. Okay, where I just put the 0 of my x-axis on the minimal point. And defined a constant omega square, which tells me how steep is this harmonic potential. Okay, so in principle, we're going over to solutions of differential equations. We have to find the solution of the h psi equal e psi, which is the eigenvalue and eigenvector equation for the stationary Schrödinger equation of this problem. And we'll do it. But first, in the remainder of this lecture and in the next lecture, we'll do it in a completely different way. That, first of all, I believe is much more fun. Second, it has a lot of physical implications. And third, it shows you the power of operators. Omega squared. These are, I can't put a constant on. I should have written here some V0, some constant here. So I write the constant in terms of m, and omega squared. Why? Because that's the usual way that one writes harmonic oscillator potential. We know classically that the frequency of mass oscillating in harmonic potential
is this.
Is this. It's proportional squared to the steepness of the potential. So it's just a choice of constant. Okay, I wrote it down in operator form. I'm allowed to do it. Now I define two new operators. Are A and A Dagger Hermitian operators?
No.
Of course not. Why?
Because you don't have
Equal.
Equal, yeah.
Exactly. X and X dagger are equal. P and P dagger are equal, but here I have a minus.
Yes.
It is the dagger operator on A, which is exactly written here, but I don't get the same operator. So these operators are not physical observables. So you can't think for a moment, why do we define it? We'll see in a moment. And these have very nice names. These are the creation and destruction or annihilation operators. We'll see, actually, probably next lecture, what do they create and what do they annihilate. But nice names. Okay. Now let's define a new operator, which is the multiplication of A dagger with A. Okay, this guy is already more interesting because it's a physical operator. Why? Because it's a remission. Why? Let's prove. By definition, remission. Okay. I want to write down this operator explicitly. Okay, so I just copy the definitions. Here it's very important to remember that x times p is not equal to p times x. And therefore I have this commutation relation which is not zero. Further question?
Yes, the commutation relation between A and A dagger.
Wait. we will explicitly, it's very important, but in a moment. Okay. Return to your notes from a lecture or two ago. But this is our good old friend, the Hamiltonian. It's 1/h². Okay, so let me write down the Hamiltonian. Sorry about it. And where did you see such a form previously? In modern physics, the energy of a photon. Just there we didn't call it n operator, but n, the number of photons, right? So, one moment. So, n is the number operator. And why do I call it a number operator? What is the connection to the form of energies that we have seen for a photon? Next lecture, as I said, today I have to finish early, so we'll stop here.